Hi there everybody, welcome back to another math video. This one is about the properties of logarithms. All right, so let's get started right away. This is going to be a information-packed video here. I want to get some basic assumptions out here on the table about log expressions first. All right, if you have a log expression, log base b of x equals y, there are some basic assumptions that we need to hold about some of those values there. First one being that the b value, the base of the log expression, is always a positive number not equal to 1. All right, now that may be a little bit curious. I'd like to explain a little bit why that's true, because you can interpret that log expression as being the same thing as saying b to the y equals x. So why couldn't I have a base of 1? Well, you could. You could have 1 to any power, and what does 1 to any power equal? It just equals 1. So it's not that you cannot, or it's undefined, it's not illegal to have a base of 1. It's just what mathematicians like to call trivial. It doesn't really do anything. It's there, it's real, but it's not useful at all. So we just kind of ignore a base of 1. And why does it have to be positive, you may be asking? Well, that's because also you could have a negative number raised to a power. It's not illegal to take a negative number and raise it to a power. So why couldn't a log have a negative base? Well, it's a really interesting question. I encourage you to explore this kind of on your own. All I'm going to say here is that for a logarithm having a negative base, sometimes it's going to give you a real number, and some other times it's going to give you an imaginary number. And so that sort of straddling both real and imaginary number worlds also makes that kind of a thing not very useful. So it's not undefined, it's not illegal, it's just that a lot of times we'll get an imaginary number, but sometimes you get a real number too. So it's a strange little niche of logarithms in mathematics, and if you're interested and curious about it, please, by all means, explore it, because it's kind of cool and kind of weird. So before we move on, I wanted to take this opportunity here to talk a little bit about log functions, because as a result of having b be a positive number, that means that x also is a positive number. All right, so the argument of the log function, the x value there, the input value, we call it also the argument. That argument is always going to be a positive quantity, a positive number sometimes, okay? So what we've done right there, and if you think about that, that makes sense, right? Because if you take a positive number b and raise it to some power, that result will always be positive as well. All right, so what we're doing here in terms of log functions is we are defining, by these assumptions, the domain and the range of a log function. And it is true that the domain of a log function is greater than 0. All right, the argument there in that log expression has to be a positive number, and therefore the domain of the log function is always positive as well. All right, and since any number can be used as an exponent, positive or negative, that means that the range, the y values of this log function here, are going to be all real numbers. So there's the domain and range right there of log functions in general, unless they've been tweaked and shifted or transformed somehow. All right, so let's talk a little bit more about this in context of exponential functions. Here's a graph of an exponential graph, the blue curve, that's y equals 2 to the x, and its domain there you see as all real numbers, and the range is y greater than 0. When you take the inverse of that and flip it across that line, y equals x, that's the green dotted line there, you get that red logarithm curve, and that actually is the equation y equals log base 2 of x. Its domain is x greater than 0, and its range is all real numbers, and so you can see right here that the domain and the range are interchanged between these two functions. Okay. In general, if we said if we have the function f of x equals 2 to the x, the inverse of that function is log base 2 of x. That works for other log bases as well. If I had g of x equals log base 3 of x, its inverse is 3 to the x. So you can say here in general that log functions and exponential functions are inverses of each other as long as they both have the same base. Okay? Alrighty, so let's get started here with talking about the log properties. And the first log property is called, they're sometimes called the laws of logarithms, all right? The first one's called the product rule, all right? And it looks like this. The log of a plus the log of b equals log of a times b. And if you wanted to put that into words, you could say that the sum of logs, a sum of logs, is equal to the log of a product. And the product is the arguments of those two logs. So log a and log b, the arguments are a and b, and you multiply them together, and that's the log of a product there. So there's the product rule. We'll see how that works out in some other examples pretty soon. Here's the second log property. It's kind of the inverse of the first one there. It's log A minus log B is equal to the log of a quotient. It's called the quotient rule because you get the log of A over B, which is a quotient. So it's the quotient of the arguments there. All right, and you could put that into words too. I'm not sure how useful saying the difference of logs is equal to the log of a quotient. It's getting a kind of a mouthful there. All right, here's the third log property, power rule it's called sometimes. And it looks like this. It's the log of a to the n power is equal to that power n times log of a. This is a really interesting little moment in mathematics. On the one side of the equation, that value n is an exponent. On the other side of that same equation, that value n is a coefficient. I don't know of another place in mathematics where that works out like that. So it's kind of a cool thing. Sometimes, because of the way this sort of looks on paper, that sometimes people call it the wraparound rule. I think that's a pretty good name, actually. It kind of shows what that n value is doing as we manipulate the symbols around in these properties here, okay? All right, so what we're going to do here next is we're going to take some applications of these properties. Here, the product rule. Here's a basic, straightforward application of the product rule. Simplifying log of 3 plus log of 15 gives us, log of 3 plus log of 5 gives us log of 15. All right, there's a straightforward application. Let's see, here's one kind of going the other direction. Log of 3x. Well, we see 3x so often in math classes that you don't maybe even think of it as a product. It's 3 times x, though, and so you could expand that out to log of 3 plus the log of x. All right, here's another one kind of like that. Again, log of a product is equal to the sum of logs. And I put this one in here to kind of illustrate the fact that log of x plus 1 cannot be simplified or expanded or changed really in any way. It's the log of a sum just kind of stays as is. It does not get simplified. All right, then here's kind of a curious one here. Log of 50. Is that a product? Well, it could be. You could have 2 times 25, or you could have 10 times 5, those are both products that equal 50. So you could take the log of 50, for example, and you could split it up using the factors of that argument right there. So I chose 10 and 5. Log of 10 plus log of 5 equals the log of 50. Now this is kind of curious here because it gives me an opportunity to mention something else about logarithms. And that is that when you see log just of some number, not log base 2 or log base 3 or log base some other value there, when there's no base written, in other words, then the base is assumed to be a 10. All right? And the log base 10 of 10 equals 1. So that log of 50 could be written as 1 plus the log of 5. That's kind of an interesting thing right there. All right, so log of 10 equals 1, and that's something that you'll get used to using. All right, so let's work on the quotient rule pretty soon here. By the way, those last 3 examples were things where we expand an expression, and the first one was where you would simplify an expression. So when you see those instructions in some of your practice exercises, this is what they mean. We'll do this again here for the quotient rule. Log of A minus log of B equals log of A over B. Here's a straightforward application of that. Nothing too mysterious or strange about that. That's pretty basic. Here's another one. It looks a little more complicated, but it's really the same thing. Log of x plus 2 minus log of 3x. You could simplify that into that single logarithm there, log of x plus 2 over 3x. Okay, there's a single log way to write that. Here's so those are both simplifications. Here's another one where we're going to go the other way. We're going to expand it out. Log of x over 3 is log of x minus log of 3. No big deal. What about log of 45? You could write 45 as 90 divided by 2 if that for some reason served a purpose in your life. So numbers can also be expanded out just by finding 2 numbers that divide to equal that argument. All right, and that's, of course, that's where we are expanding log expressions. Okay, let's work with the power rule here a little bit. Some interesting things going on here with this one. Log of x squared equals 2 log x. It looks pretty basic there, taking the 2 as the exponent there and wrapping it around to get 2 times log of x. Just want to comment here on this. Log of x squared is the same thing as log of x times x. So if we use the product rule and split up that product product, x times x, you could say log of x plus log of x. Well, I'm taking log of x and I'm adding it to itself. So now I got 2 log x's. So that's another way of looking at that power rule application right there. Let's see, what about this one? Log of a to the negative third. That's just negative 3 times log of a. All right, no big deal right there. Power rule, the wraparound rule being applied there. What about a square root? Is a square root using power rule? Well, yes, it is, because you can write the square root of a number as that number to the 1/2 power. So you could write that log of the square root of x minus 3. You could simplify that out to being 1/2 times the log of x minus 3. All right, let's look at another one kind of like that. In a sense, log of 1 over x, well, that doesn't look like an exponent or a power or anything like that. But you could, if you think about 1 over x, you could think of 1 over x as being the same thing as x to the negative 1 power. So there it is, an exponent. And we can write that log of x to the negative 1 as negative 1 times log of x. So there you go. Or I could have split that up as a quotient, all right? Would I get the same thing, you may be asking, if I wrote that 1 over x as log of 1 minus log of x? Well, yes, actually it would, because the log of 1, that's log base 10 of 1, and so 10 to what power equals 1? Well, that has to be then a 0. So log of 1, no matter what the base actually, is equal to 0, and 0 minus log x just equals negative log x. So yeah, we get the same thing. Either way we interpret that log expression there, 1 over x. Okay? All right, so here's what we're going to do here to finish up this longish video is do a couple of, several examples here of combining these log properties together. And this is going to be one of the more challenging parts for you in this practice here of learning how to deal with logarithms, is that the fact that these properties can be sort of interwoven and combined in various ways. All right, so here's an expression, log of 3x squared. And what we're going to do is expand this expression out so that we have just logs of a number. No log of a power, no log of a product, no log of a quotient. All right, when we're done, that's what we should get. So log of 3x squared, that's a product, 3 times x squared. You could write it as a sum of those two logs. But then we've got log of a power there, log of x squared. So we can rewrite that as 2 times log of x. And there we're done. No log of a power, no log of a product or anything, just log of 3 plus 2 times log of x. That's this simple expansion as we can get. All right, let's try this one. Here's a product. This one looks pretty scary there. But first, let's take it in phases, okay? We can use the quotient rule there. Well, I guess we're kind of using the product rule as well. Log of the cube root of x minus the sum of those two logs, log a plus log b. Now, just like the square root could be 1/2, the cube root could be 1/3. So that's 1/3 times the log of x minus log a minus log b. That's one way to write that expansion there. All right, let's take a look at another one like this, because this is worth dwelling on just a little bit. So there again, the square root of 5 over 7 times x. So I could sort of take that as 1/2 log 5. Minus the sum of log 7 and log x, or I could distribute that subtraction to the log 7 and log x and write it without the parentheses there. Your choice on this kind of a thing, folks. Whatever you feel is the preferred way of doing it, that will be good. All right, well, let's now go the other direction where we're taking log expressions that are like long drawn out things and try to simplify them or compact them into a single log expression. All right, so here's one pretty simple here. Log of 5 plus log of 2 equals log of 5 times 2, log of 10. This is pretty unremarkable in one way, but in another way, this is kind of strange because log of 5 is an irrational number, and so is log of 2. And so this is one strange case where I'm taking the sum of two irrational numbers and I get log of 10, which is actually a rational number. All right? Kind of unusual, kind of surprising, kind of wow, you know, adding two irrational numbers and it equals a rational number. That doesn't happen all the time. All right? So I just thought that was worth mentioning. Here's another one. say I've got this subtraction of 2 logs right there, 3 times log of x minus 1/2 log of y. Well, let's see, I can use the wraparound rule here kind of in reverse and write it as log of x cubed minus log of square root of y. But let's keep going. Let's write it as a single logarithm of x cubed over the square root of y. There you go. That's a single logarithm. Now, that would be good enough for most people, good enough for me, but for some people, they don't like to see that square root on the bottom of a fraction. So rationalizing the denominator of that fraction would give you this expression, and I'm just putting the question to you, which one do you like better? Which one is better? Is it better to have that square root on the bottom or have the square root on top? I don't really know. It's kind of a matter of opinion. Whatever you think is good. I'm good with either one. Let's do another couple of them here. These are a little bit simpler, but they illustrate this idea that came up in the last set of examples as well. Log of a minus log of b plus log of c. Okay, so we can write that as log of a quotient, ac over b. Why is it ac on top? Well, both of those logarithms, log a and log c, are both positive, so their arguments will go on the top of the fraction, and since log b is negative, its argument goes on the bottom. If I change that expression just a little bit by adding some parentheses there, that changes my result. Okay, now I'm going to have just a is the positive one, and b and c will be, since those logarithms are negative, the b and c go on the bottom of the fraction. Okay, well, that, like I said, was kind of a longish video. I hope you stuck with it to the end. Sorry for talking so fast, but there was so much material here to talk about on logarithms. It's a big topic. Hang in there, folks. Practice, practice, practice. And you will get it figured out. Okay, it is a complicated system, but it's a closed system. You can learn all of the stuff here in this log property system. And so thanks again for watching, and be well. And I hope I see you soon. Bye bye.